Lahore, Punjab, Pakistan. This international webinar is jointly organized by the Department of Chemistry and IQAC of our college. The topic is international webinar on photocatalytic CO2 reduction challenges and perspectives. This topic is a different one. In the lockdown situation, Mrs. S. Kavita, Dr. V. Selvam, Organizing Secretary, Assistant Professor of our college, has taken earnest efforts to organize this international webinar on today, 17/8/2020. Hearty congratulations and welcome to Mrs. S. Kavita and Dr. V. Selvam. Also, my best wishes and welcome to the organizing committee members, Mr. T. Jayapal, Dr. V. Gomadinayagam, Dr. C. Anita, research scholars, students, and participants from various institutions and our college. My hearty welcome to Dr. K. Balasubramanian, IQAC coordinator, and Mr. Subhash Chandra Bose have given their technical support. Once again, my sincere welcome to one and all. After completing this webinar, all the participants are asked to give your valuable suggestion. Thank you very much for giving the opportunity. Now I hand over the session to Mrs. S. Kavita.
Thank you, sir. And we invite Dr. Battanasamy, sir, to facilitate. KB, sir.
I think he was not in. He's not in line. Ma'am, I think he's not in line.
Selvam?
He's not in line, ma'am. Battanasamy sir not in line.
You may proceed.
Yeah, KB, sir.
No, madam.
You call Battanasamy, sir.
But you can continue. You can. Both are not in line. Both the persons are not in line. KB sir and as well as Battanasamy sir.
1 minute. You'll wait. The Battanasamy sir will come, I think.
Okay.
Can you able to hear my voice?
Yes, ma'am. Okay.
Yes, ma'am.
Okay. I think Bethanasamy sir is online.
Yes.
Yes.
So on behalf of Mr. G. Bethanasamy
Sir, one
and
minute.
Dr. K. Balasubramanian, I wish to record my best wishes for organizing such a nice type of international webinar. Now the session handed over to the organizing secretary, Dr. V. Selvam.
Thank you, sir.
So, Dr. Selva, my voice and screen, everything is okay to start?
What's up?
Wait, sir. Handed over to Dr. Selvam.
Yes, madam. Thank you. Now, ask the resource persons, Dr. Only to give the presentations. Please start, sir.
Selvam.
Yes, madam.
Person.
Dr. Selvam, I think, can you hear my sound, voice, and screen is clear?
Good morning to all.
Now, you can start the
Good
presentation,
morning
sir.
to all, especially our chief guest resource person, Dr. Shashat Ali. It's my pleasure to introduce Dr. Shashat Ali, a man of simplicity and wonderful human being, good researcher, very good academician, and good teacher. So I'm very proud to say our resource person is Razat Ali. He did his BSc in chemical engineering at University Lahore, Pakistan, and also he did his MS in chemical engineering from Source University Lahore, Pakistan. During his MS in chemical engineering, he got award for the merit. He is awardee of HEC USA ID merit-based scholarship. His thesis on protection of biodiesel from microbubbles. His research in energy science and engineering, that is from DG Institute of Science and Technology, South Korea. The research on the basis of synthesis of efficient and economically viable photocatalyst for CO2 reduction.
Yeah,
Dr. Sasas Ali has so many responsibility in Comsats University, Lahore, member of Central Analytical Lab, Chemical Engineering Department. He is a director in operation and maintenance of analytical instruments, XRD, GC, NMR, HPLC, AAS, and basic interpretation of result originated from these instruments. And also is a member of Microfluids Research Group, working on biodiesel and ethyl acetate production using novel microbubbles. And also, he's a teacher in the Department of Chemical, Swedish Institute of Technology, Pakistan. Now he is working as a professor in Comsats University, Lahore, Pakistan from 2016 to till date. Apart from this, he is also having the industrial experience. He was an assistant engineer, Harris & Co., an engineer contracting Pakistan from March 2010. He has excellent characterization technical skills. He did a special course on energy, the big picture from Sadia Technical Institute, USA. Apart from this, is a manufacture and simplicity. Apart from the academic achievements, he's a good human being. When I collected the information from his friends, at that time I was surprised. Why? He is having the tendency to helping others who were students for the education consistently. My hearty congratulations, sir.
Thank you, ma'am, for such a nice introduction.
Because of virtues and values that was developed and
Thank you,
nurtured
ma'am.
during his student's life. If
Thank you, ma'am.
one
Thank you.
takes a
Thank you
close
for
look at the alchemy and achieving person, do distinct virtues pop up besides perseverance and hard work. So he's a living inspiration to the young students and researchers. With this, he published so many publications, journals, and also papers in the reputed journals. And also he attended so many seminars, he arranged, organized workshops. And also he's having the character skills courses. He learned the course, Energy, the Big Picture from Sajia Tech Institute, USA. So I thank Dr. Zazat Ali for immediate acceptance for this. I welcome you, sir, Dr. Zazat Ali, and also I welcome our college principal, Dr. A. Subramanian, and Dr. Bettanasamy and Dr. K. Pala Subramanian, IQAC coordinator, and also other registrants from China and Qatar and other countries, and also the registrants from various states and the registrants from Tamil Nadu and from MD Hindu College, Tirunelveli. I welcome you one and all. With that, I thank our college management for this wonderful support, organized support for this. With this, I conclude my introduction of our wonderful person, human being, my friend Zazat Ali. Over to our resource person, Zazat Ali. Sir, thank you.
Thank you. Thank you, madam. Thank you, Dr. Sabriman and Dr. Salvam for arranging this talk. And I'm really thankful to you, ma'am Kvita, for such a nice introduction. So I will start my talk, which is related to photocatalytic CO2 reduction challenges and perspectives. It's a wide range of talk, which is covering all the aspects of CO2 reduction in generalized manner. So I'm working as a research associate in Concepts University, Lahore. It's like a faculty position, which we have to do research as well as we have to contribute for the academic courses. So I did my BS and MS, as Ma'am Kavita told, from the same department where I am working, and I'm doing PhD from Energy Science and Engineering Department, DJs. So my talk will be consist of the economic and environmental impacts of CO2 reduction, CO2 reduction technologies, photocatalytic CO2 reduction, and challenges in photocatalytic CO2 reduction, and how we can solve this CO2 prevalence, and what economical and viable photocatalyst I have produced for the photocatalytic CO2 reduction. And lastly, we will have a conclusion about the future direction and question and answer. So first of all, I will start with the CO2 emission and the fossil fuels linkage. So you can see in this picture, there is a strong relation between these two. As the world's energy demand is increasing, people are consuming more and more fossil fuels, which is producing more and more CO2 emissions. So as we know, the world's population is increasing. So we are strongly anticipating that the CO2 emissions will increase. So the CO2 concentration increase is so high that it has reached 407.4 ppm in 2018. So just within 1 year, the increase was 2.4 ppm. So as world energy is touching a huge amount consumption, so we have to avoid the fossil fuels, or we have to reduce the CO2. So these are the challenges which we are facing using fossil fuels. So what CO2 can do for us, like we can produce like economical benefit. If I say what we can do, if we are able to reduce CO2 efficiently, we can produce syngas. If we can produce synthesis gas from this, then we can produce every kind of fuel through Fischer-Tropsch synthesis. Like just we have to need carbon monoxide and hydrogen. From this, we can produce like lower olefins, gasoline, diesel fuel, jet fuel. So every kind of fuel we can produce by this Fischer-Tropsch synthesis if we can reduce CO2 and water to syngas. So we can produce high value olefin. So we can see that carbon monoxide has a market value of $0.06 per kg. But if we produce propane from this, we can have a value of $8 per kg. So you can see there is a huge difference between the price. So we have to go for the higher chain hydrocarbons from CO2 reduction in order to get the more economic benefit so that we can commercialize this technology. Because for commercialization, economy is very important. Nobody will be ready to invest if we will not have a commercial viability of any chemical process. So another problem is that, wind energy, solar energy, its price is decreasing, and there are so many plants which has been installed and which will be installed in future. So we will have a lot of energy from the sun. But the issue is that we can utilize only this energy in the daytime. For storing solar energy for night, we need a big storage mechanism, which is also an energy intensive process. So how we can store the solar energy, it's in an economical way, it's again a challenge. So I will conclude in my next slides that how we can overcome these challenges. So what are the environmental benefits if we can reduce CO2? So well, Earth temperature is increasing. And acidic rain is also a cause, which is like CO2 is also contributing, which is corroding, erosion the soil. And the greenhouse gases, like CO2 is a greenhouse gas. When the light comes, it absorbs light and when leave very few of the sunlight to go back into the environment. That's why Earth temperature is increasing. So another perspective we can have if we can reduce CO2 is the cleaner chemical processes. Like if we know that how we produce the fuels from biomass, you will be familiar that we use the fermentation process. We ferment the sugars to produce the methanol, and then we use it as a blend in the gasoline. But if we are able to reduce CO2, we can directly convert CO2 to fuel, so we need no need of fermentation, and fermentation itself also produces CO2. So we can avoid these steps. So these are the economic and environmental benefits of reducing the CO2. So how we can mitigate the CO2? It can be like there are two sources, like either we have to use renewable energy, either we have to increase the energy efficiency of the process. If we are unable to do that because the pace is very slow, renewable energy, our conversion from fossil to renewable is very slow. So this doesn't look an attractive option in the future. Surely it will help, but it's not be able to like mitigate all the CO2 which we are producing. So the other way is the improving the energy efficiency of the process. So still people are working over it. We are having more energy efficient processes which produces less CO2. But the adoption to these technologies is very slow because efficient equipment, efficient process, they will have a more economic value. We have to pay more for that. That's why their adoption to these technologies, especially underdeveloped country, it's slow. So then what is the viable option? The viable option is to reduce the CO2. So how nature responds to this perilous gas? Nature reduces CO2 by photosynthesis. What photosynthesis? You all are familiar. The plants harvest carbon dioxide in the presence of sunlight. to carbohydrates, which are used by human beings, animals, and all of our uses. Like, so photosynthesis is very slow process. The amount of CO2 which we are generating is too much as compared to the amount of CO2 which plants are intaking to reduce the CO2. So then, then we have to go for a synthetic process. We have to like invent some novel technologies which can reduce the CO2 more efficiently so that its production, so it can match the production rate of the CO2. So the main conclusion is that we have to invent such a processes which can efficiently and quickly can convert CO2. So for this, what are the suitable method until now people are using? Like, we can use thermal splitting and electrical splitting. In electrical splitting, we are using plasma catalysis, electrocatalysis. But the issue is again that these technologies need energy. And this energy is again interlinked with the fossil fuels. So again, we are going to CO2 emissions if we will use this technology. So except thermal splitting, we can reduce pure CO2. As CO2 is a stable molecule, it's very difficult to destabilize it. So it needs a lot of energy. It again needs energy. If energy is not from renewable, this process is again not a promising option. Then splitting with co-reactant, we can do the dry reforming of CO2. These are the exothermic processes that can be done easily, but again, we need the methane and we need the CO to reduce it. So these technology, if they are not using energy from the renewable resources, that is not good for the CO2 reduction. So then another option is we can do the photoelectrocatalytic solar thermochemical. In solar thermochemical, what we do, we reduce the metal oxides like TiO2. Cerium oxide is widely used in this field. So we reduce it with the help of solar energy. So when it is reduced, then we can add water or CO2 at high temperature. Then what will do, they will oxidize this reduced metal oxide and they will reduce to hydrogen. Water will reduce to hydrogen and carbon dioxide will reduce to CO. But this is very energy intensive process, almost 800, 900 degrees Celsius temperature we have to achieve. For this, we need a very sophisticated photocatalytic reactor and a very good setup for the solar light concentrations. So this is again a very expensive technology, but it seems promising because it's using sunlight. So another is photocatalytic. Just we can use the sunlight. It's similar to for our natural photosynthesis. Biochemical, algae can harvest CO2 and other processes. We have industrial uses of CO2, like we can produce urea from the CO2. So all these processes are lucrative, but to me, photocatalytic seems very interesting and very promising technology because it's just like artificial photosynthesis. What we do in photosynthesis, we can do in the photocatalysis. So photocatalysis is what we do. We use carbon dioxide, water as a reactant. So these are very cheap reactants abundantly available in the universe. We do that. We provide the sunlight and the presence of the photocatalyst. Then we are able to convert it to solar fuels or chemicals. So this, according to this picture, this cycle is looking close cycle that CO2 is getting produced, then again it is converted photocatalytically, then it is used again as a fuel, again produced. So it is a closed cycle. It seems very promising, very attractive technology that everybody can install and produce their fuels, but it's not so easy. Why it's not so easy? Because reducing CO2 is a thermodynamically challenging step. It requires a huge amount of energy. It has a positive Gibbs free energy of 818.3. So it's a big energy barrier for crossing CO2 to produce methane, ethane, and other solar fuels. So this barrier has to be crossed to convert it into fuels. So it's very, but with the help of photocatalysis, it can be done at ambient temperature, ambient pressure. We no need of light concentration as we use in solar thermochemical. So it's it seems promising in this way. So how we can do the photocatalysis? For a photocatalytic cycle, how it starts? First, when light get incident over the surface of the photocatalytic, it produces holes and electrons. Holes remains in the valence band of the semiconductor, and electrons migrate to the conduction band. And these holes and electrons, they are the reactive species which we can use for our photochemical reactions. So what we can do then, these holes can reduce the oxidized water to oxygen, and these electrons can reduce CO2 to solar fuels. Again, it seems very promising, but it's very challenging. Why it's very challenging for semiconductors? If we see the reduction potential of a CO2 molecules is minus 1.90 volt. So if you see the conduction band position of all the photocatalysts which are existing in the universe, none of the photocatalysts possess this highly energetic conduction band. So, you know, the famous TiO2, it around maximum 0.8, minus 0.8, like copper has a minus 1.2, minus 1.1, but still achieving a conduction band of minus 1.90 volt is not, hasn't been achieved. So it's a big challenge for photocatalysis. Then what we do to solve this issue? We use the proton coupled CO2 reduction. So this reduction potential is reduced when we do the CO2 reduction in the presence of the protons. And from where these protons come from the oxidation of the water. So when protons and electrons are available for CO2, so you can see that the reduction potential is considerably decreased. Like for CO is minus 0.53, for methanol is 0.38, for methane it's minus 0.24. So it got decreased when we do in the presence of the protons. So now we should understand that how we can do the photocatalysis. We need sunlight, we need a catalyst with a suitable valence band and conduction band, and we need the water as oxidizing agent. We need a sunlight which can produce the electrons and holes. So as we have seen the picture behind, we see it's very interesting and very eye-catching process. But for every idea, when it converts into invention, then we have to convert into innovation. It needs lot of effort. You can see the wheel has been invented decades, hundreds years ago, but now the wheel is used in the cars everywhere. So from invention to innovation, it takes time. So CO2 reduction is also an invention, but to make it as an innovation, there are challenges. What are these challenges? These challenges is that the photocatalyst, like if we see economically cost photocatalytics shouldn't be expensive. It should absorb much light. It should show like wide range of applications. It should have a good contact. Then we must have a good reactor. So these are the challenges. So how these challenges can be solved? Like limited light, if the band gap of the catalyst is very high, it can harvest very small amount of solar light. Then we have how we can use maximum solar light. We can do the band gap engineering. What in band gap engineering, what we do, we add impurities, we reduce the catalyst, we photosensitize it, and then if the first step is completed, we are able to produce a catalyst more number of electrons and holes. Then issue arises, these electrons and holes, they got combined with each other. So instead of we utilize them for the chemical process, for water oxidation, for CO2 reduction. They are combined. So before their combination, we have to use them. That's why we have to avoid the recombination. Then how we avoid the recombination? We use co-catalysts, metals and non-metals. We make the heterostructures for reducing this charge recombination. And then again, our reactant in every catalytic processes, it's very important that the reactant should adsorb over the surface of the catalyst. If the reactants are not adsorbed over the surface of the catalyst, it's very difficult to produce a chemical reaction. So for CO2 adsorption over the surface of the photocatalyst, we do different modifications, alkali modification, surface functionalization. Then photoreactor design is very important. And another issue which I have talked earlier, that producing carbon monoxide doesn't have so much economical benefit. But if we are able to produce a propane, our income could increase 45 times more. So we have to go for the higher hydrocarbons. For that, people are using solar light concentration. They are using such a techniques which can stabilize the intermediate products. So according to these surface modifications, to me, heterojunctions construction, metal deposition, and impurity doping. These two, three techniques, surface modification looks to me promising. So I will start with the metal deposition. Like metals mostly have a Fermi level below the conduction band of the semiconductors. So if the metals have lower Fermi level, then what will happen when light will strike, it will produce holes and electrons. Then metal, they are used as electron sink. Then electron will migrate to these metals, and the metal will separate these electrons from the holes. So when the electrons are separated from holes, then they are available for the photocatalytic reaction, and our efficiency of the reaction will increase. Another way metal provides reduces the band gap. Also, what metal do, they produce the surface Plasmian response. In surface Plasmian response, what do metals absorb the light? When they absorb the light, they produce the electrons, and they provide these electrons to the surface of the photocatalyst. Again, we have a more number of electrons available for a photoreaction. So both way metal, either by surface Plasmian response or either as using as electron sink or trap, they are the beneficial for photocatalytic CO2 reduction. Another thing is the heterostructure formations. Like we see in previously that holes are used for water oxidation, electrons are used for the CO2 reduction. So what we do, like some catalyst has very energetic conduction band. If conduction band is more negative, it is more good for the CO2 reduction. And if a valence band is more positive, it is more good for the water oxidation. So this means we should have a catalyst which has a high negative reduction band and highly positive conduction band, a valence band. Both way the catalyst can produce CO2 reduction efficiently. So, but if we look at the division of the catalyst, if you see in the picture, some catalysts, they have a very good, very energetic oxidation valence band, and some catalyst has a very energetic reduction band. So heterojunction formation provide us the opportunity to use the both features of the catalyst. Like we use two catalysts. One catalyst has the very strong oxidation potential. I means the positive valence band. The other photocatalyst has a negative reduction potential like conduction band. So when we combine together, they form the heterostructures. When they form the heterostructures, then two types of heterostructures can be formed. Like type 2 heterojunction. What happens in type 2 heterojunction? Electrons are transferred from the higher reduction potential to lower reduction potential, and holes are transmitted to these from the highly positive to less positive valence band. So electrons accumulate there, holes accumulate there. In this way, they are separated and they are used for the photocatalytic CO2 reduction. But you can see in this way, both catalysts can harvest light. So large part of solar light we can use. But and also charge separation is achieved. But the issue in this type 2 heterojunction is that while electron transfer from higher reduction potential to lower reduction potential, they lose their energy. Similar for the holes. So then, well, less strong electrons and less strong holes are available for CO2 reduction, which is not a requirement for an efficient process. Then what we do? Then the efficient way is to construct a Z-scheme heterojunction. In Z-scheme heterojunction, what we do? In Z-scheme heterojunction, like we combine two catalysts, which one is oxidation catalyst, one is reduction photocatalyst. Then electrons from the lower negative conduction band transfer to there. They combine with the holes of this semiconductor. They combine with each other. These weak electrons and weak holes, they are neutralized. Weak electron and weak holes, they are neutralized with each other. So resultantly, what we have a negative, we have more negative electrons survived, more positive holes survived, which are used for photocatalytic CO2 reduction. So this way we can use them very efficiently. They also improve the stability of the photocatalyst. These scheme heterojunctions are very famous and very good for the stability. I will explain in my next slides that how good they are for stability. So this is the work, sustained photocatalytic CO2 reduction to methane in continuous flow reactor by earth abundant materials. This is the recent work which I published in Applied Catalysis B. Here, what I will use the economically viable catalyst with the good reaction with good geometry, which I have explained Z-scheme heterostructure. So I use TiO2 photocatalyst. Why? Because it is abundant, non-toxic, its cost is low. Its valence band and conduction band are favorable for CO2 reduction. So what I did, why I reduced the TiO2. While I reduce the TiO2, what happens? Its band gap is reduced. When its band gap is reduced, it can harvest more light. Then I use the copper as a co-catalyst. As I explained in the previous slides, that the metals are used as a co-catalyst. And I have also explained how the metals are important. They act as a electron sink. So they are good CO2 absorbent. Copper is a good CO2 absorbent. It is electron sink, so it can separate electrons and holes. So it can also reduce the band gap. Also, the intermediate products which are formed, it can stabilize them. Like instead of converting CO, we can get the methane and higher hydrocarbon products. So this is the synthesis scheme, how I have synthesized it. I took P25, commercial form of the TiO2. I used, it's very thermochemical process. I use sodium borohydride at 350 degrees Celsius. Otherwise, we have to give a high temperature if we will not use the sodium borohydride. So I reduced TiO2. Then in the presence of sunlight, I just deposited the metal part, copper, over the surface of the TiO2. What I got then, according to the TEM images, when I reduce the TiO2, then only the edges of the TiO2 are reduced. Its core is the crystalline, but it has a disordered shell. So this solder shell is efficacious. It's efficient because it can trap the electrons. When it will trap the electrons, they will survive from recombination. So I can see clearly that the copper 2 oxide is deposited only on the edges, not over the surface of the TiO2. So we're on the edges, and edges are reduced. So electron density is high over the edges because the edges of the TiO2 are amorphous. They can trap the electrons. So interface between copper and TiO2 is formed. So clear interface can be visible. So now this is the like interface. Like if we see the core shell heterostructure, in core shell what we see, like there is like one semiconductor, and over the surface of it other semiconductor is wrapped. So the underneath catalyst cannot participate in the reaction, but here you can see both surfaces are exposed, so they can take part in the chemical reaction. So I took UV of that, but I've seen that after reduction, its valence band, its band gap is reduced. So it's for P25, it is for the reduced titanium. But after copper deposition, the valence band, the band gap is not reduced considerably. Then I find their valence band and conduction band positions using a combination of UPS and the top plot. From this, I draw the band gap diagram. So band diagram, you can see here, the valence band of the reduced titanium is minus 0.48. And the valence band, conduction band of the copper 2 oxide is minus 1.08. So it is more negative than that. And this is RT valence band is more positive than the valence band of the copper 2 oxide. So if we go to the previous slide, which I've showed, the heterojunction, it's same, like RT is here and copper is here. So what I've seen that here heterostructure is formed there. So then I did the XPS to check what are the chemical oxidation states. I have seen after reduction, the binding energy shifts to the lower binding energies. So when the binding energies are shifts to lower binding energies, this means TiO2 is reduced. So Ti4 plus sites are converted into Ti3 plus sites. So Ti3 plus sites and oxygen vacancy, when TiO2 is reduced, they are good for the CO2 reduction. I will explain in the next slides how they are efficacious. So I also did the XPS to get the copper oxidation state. So initially I have seen the copper oxidation state is +1 or 2+. But after photocatalytic CO2 reduction, I have seen the copper binding energy has shifted to lower binding energy. Previously it was 932, then it was shifted to 931.3. This means after photocatalytic CO2 reduction, copper is reduced. How copper is reduced? Because electrons from the TiO2 are transferred to the copper. How they are transferred, I will explain in the next Z scheme. I have already explained how electrons are transferred in Z scheme. So I did EPR. With the help of EPR is the electron paramagnetic resonance spectroscopy. With the help of this, we can see the paramagnetic electrons. Like if the spin of the electrons in orbital is opposite, so they cancel each other's effect. So if only one electron is present in the subshell, then what will happen? It will have some magnetic field which can be detected with the EPR spectroscopy. So I have seen before photocatalytic CO2 reduction, I got a G value of 2.1, which corresponds to copper 2+. But after photocatalytic CO2 reduction, it is reduced. And this means copper +1 is reduced to the copper 2+ is reduced to the copper 1+ or copper 0. So from XPS results, I've seen electrons are transferred to copper, and from the EPR, I've seen copper when electrons are transferred, copper is reduced, so it changes its oxidation states from +2 to +1, then finally to +0 state. So what I've got from the XPS that TiO2 is reduced, it has Ti3 plus states, oxygen vacancy, and copper is reduced to +1 to 0 state. Then I did the PL studies. This is the steady state PL. What I got in PL, that after reduction, the electron PL studies, actually what they tell us that how much time the electrons and holes are separated. So indirectly it tells us the electron and hole recombination. So if intensity is high, this means the electron and hole recombination is more. But P25 after reduction, intensity is reduced. This means that after reduction, the TiO2 is able to separate the electrons and holes. So when I did the copper deposition here, you can see the intensity is more decreased. This means we have already seen copper is a metal, it acts as an electron sink, so it can separate the electron. Then I did the TRPL. TRPL tells us the time for which the electrons and holes remain isolated from each other. So from this, the trend is same as with the PL results. So from both, we conclude that electrons and holes are separated with each other. Then I did the coumarin dye test. In coumarin dye test, when I detected that electrons and holes are separated efficiently, and a Z scheme is formed between reduced titanium and copper 2 side. So then from the charge transfer mechanism, I did the photocatalytic CO2 reduction. Photocatalytic CO2 reduction, what I did, I used CO2, water in the reactor, and I shined the light over the surface of the catalyst. So I've seen from P25 to RT, the P25 doesn't produce any methane because we see its band gap is too high, so it cannot harvest light efficiently. And then after reduction, its band gap is reduced. It has Ti3 plus states and oxygen vacancies, which can be utilized for the CO2 reduction. That's why it is producing methane. Then we see the optimum deposition of the copper for 0.75 sample. We get maximum amount of methane, which is 77 nanomole per gram per hour. So we did metal deposition. Then what we did, we optimized the copper TiO2 reduction. We used different masses of sodium borohydride. So sodium borohydride, if we use more sodium borohydride, TiO2 will be reduced more. So we see if we do more, if it reduces more titanium, then the efficiency of the catalyst is reduced. So optimum number of defects like optimum reduction is and optimum metal doping. So two things are needed for the better performance. Optimum defects mean optimum reduction degree and optimum metal deposition. So also the copper oxidation state is very important for the CO2 reduction. We have seen our copper, which was initially in +2 or +1 state, after under the action of photocatalysis, it was converted into +0 state. So we see from this diagram, we can see that when the copper is reduced from 2 plus to 1 or 0 state, its performance is increased. So oxidation states, we've controlled oxidation state nicely with the help of sunlight. So so from until now you have seen I did all the processes using sunlight. Why? Due to the economy. Then stability of the catalyst is very important. If you make a material, if you make anything, it should be long lasting. It should produce long lasting results. So I checked the stability of my catalyst. So what I have seen, the stability is increased up to 7 cycles. So why the stability is increased? If you remember, I have told already in the previous slides that for the Z scheme formation, the stability got increases. Why stability got increases for the Z scheme information scheme? I will explain here. Like according to the band diagram, electrons from the surface of the reduced titanium are transferred to the copper 2 oxide surface, where they quench the holes. You know, these holes are not good for copper. Why? Because these holes have so much oxidation potential that they can oxidize the copper. When copper is oxidized, it is not suitable for CO2 reduction. So we have to avoid these holes. If we will not able to hold these holes, they will oxidize the copper. So according to Z scheme, the electrons are migrated to the copper where they quench the holes of the copper, which are not good for the stability purposes because they oxidize the copper. So they are quenched. When they are quenched, they are left no electron holes available which can oxidize the copper. So when holes are now oxidizing holes are killed, we have a very stable Z scheme. That is why we got the performance up to 7 cycles. So Z scheme formation is very important because of 3 benefits. One, you see, previously I've told more negative reduction potential. Now CO2 is reducing over the surface of the copper with reduction potential of minus 1.08. So previously with the help of RT, it was minus 0.48. So due to Z scheme, we have a very strong conduction band. Similarly, now water will not be oxidized here. It will be oxidized on the valence band of the TiO2. This valence band is very strong. So what we got the stability, we got the strong reduction and oxidation potential, and what the third other thing is the efficient charge separation. You can see this has only electrons, this part has only holes. So electron and hole recombination is avoided. So these are the 3 key benefits which we have with the Z scheme. So next comes to the mechanism. If we see the mechanism, I assume that CO2 convert first to carbon monoxide. This carbon monoxide then converts to methane, then a methyl radical. Then this methyl radical is converted to methane. And similarly, water is oxidized to produce the protons. These are the same protons which we use in reaction 1, 2, 3. And also it produces the oxygen. So it is similar to photosynthesis, where we get oxygen from the plants, we also get oxygen from the photocatalyst surface. So this is the mechanism which I have proposed, how CO2 is reduced. So in my previous slides, I have explained Ti3 plus sites and oxygen vacancy is very important for CO2 reduction, because when CO2 comes there, it absorbs over the surface of the catalyst. So oxygen vacancy helps to absorption of the carbon dioxide. So when carbon dioxide get absorbed, what happens? Carbon dioxide is a linear molecule. It has no dipole. So it's very difficult to reduce it because it's non-polar. But when it is bent, its LUMO level is increased. When its LUMO level is increased, its structure is bent. When its structure is bent, then it becomes easy to transfer electrons, as here you can see in the step number 2. Then electrons, after bent, electron can be transferred to the carbon dioxide. When the carbon dioxide electron get transfers, it converts into carbon monoxide. When it gets converted into carbon monoxide, then it can be converted into methane and other molecules. So this mechanism I've proved with the help of the characterization, like I detected carbon monoxide with the help of GC. I detected methyl radical with the help of FTIR. and I detected there is no hydrogen production. This means all the H positive ion used for the CO2 reduction. And one important thing is I did the isotopic test. In isotopic test, instead of 12 CO2, we give the 13 CO2. So what is the purpose of doing the isotopic test? Actually, while synthesizing photocatalyst, we use so many organic compounds. These organic compounds are adsorbed over the surface of the catalyst. So when we do the CO2 reduction, then methane will mostly do not come from the CO2. It comes from these organics which are adsorbed. So these organics are impurities. So we have to check whether our catalyst is reducing CO2 or this methane is coming from the organic contaminations which has been absorbed over the surface of the photocatalyst. For this, these organics are 12 carbon. So, but when we will give the 13 CO2, it will produce the 13 methane. So 13 methane will have a different atomic mass. So we use the mass spectroscopy and we confirm that methane is formed, which tells us that our CO2 is also being reduced by this catalyst. So this is called isotopic labeling experiment. It's very important and it's very good tool to guarantee that our catalyst is capable to reduce the CO2. So this is that was the work which I have did. Now I will give the some future directions that which materials are coming in the future are more attentive. People are more inclined towards the materials like single metal atom catalysts nowadays are in news, because single metal atom catalyst we have to use very small amount of metal, and that metal can be incorporated into titanium surfaces like TiO2. So these single metal atom catalysts at the atomic scale we give us a very good yield. Magazines are the 2D materials. These are basically titanium, aluminum carbide. They are first synthesized at high temperature, then they are oxidized to produce the water molecule to TiO2. So magazine, single atom catalyst, they are becoming increasingly important. So now coming about to the commercialization of this technology, until now it doesn't seem it will be commercialized in near future because there are so many challenges like product selectivity. We get so much products like when we reduce carbon dioxide, we got carbon monoxide, methane. So selectivity is poor. So this is the very big issue nowadays we are suffering. Stability, as I've explained, stability of the photocatalyst is and the cost. These three things. And fourth thing is higher hydrocarbons. Producing higher hydrocarbons like C2, C3, like propane, butane, methane is like easy to produce. Carbon monoxide is easy to produce, but higher hydrocarbons are difficult to produce because we need more reduction potential. If we need very strong electrons, and then the product like methyl radical I have explained in my previous slide. If I show you, like this is the intermediate methyl radical. So if we are able to stabilize this methyl radical, we can combine different methyl radical and we can get the long chain compound. But it's very difficult because this is very unstable. Methyl radical is very unstable, so it cannot be stabilized easily. So few studies I have seen, like people are using graphene and copper for stabilizing, but still it's very challenging. So if we are able to stabilize these intermediate products, we can get the higher hydrocarbons. If we are getting higher hydrocarbons, definitely we will get the high revenues, which will ultimately facilitate. So thank you for your attention. That's all from my side. And thank you for your time. You people listen to my talk. So now I move to question answer session. If some questions, I will be happy to answer.
Thank you, sir. Thank you. Thank you for your nice presentation.
Thank you.
Participants, if there are any questions, you can put your questions in chat box. Dear participants, do you have any questions? You can put the questions in chat box. Check that. Hello. Thank you, sir.
Yes, I got one question that why the catalytic efficiency is reduced at the 7th run.
Yes, sir.
So while we regenerate the catalyst, we take it from the reactor, we anneal it. During regeneration, some catalyst is lost. But in my case, what I have concluded, if you see if I show you the slide, I have shown you that the oxidation state is very important because copper +1 oxidation state is efficacious, good for CO2 reduction in my case. So if you see the XPS results here, that before CO2 reduction, binding energy was 932, and after CO2 reduction, it is 931. This means my copper is reduced. Its +1 oxidation state is changed to copper 0 oxidation state. So when the oxidation state is changed to copper 0 oxidation state, then it is there no longer Z scheme no longer exists. So I lost the suitable oxidation state. That's why in 7th run, the photocatalytic efficiency is low.
Thank you so much, sir.
Thank you. Any other questions? Sir, another one question.
Yes, one question I got, have you obtained any other long chain hydrocarbons along with methane? Yes, as I already explained, copper is capable to stabilize some methyl radicals. So I got ethene and ethane, but in very low concentration because stabilizing methyl radical for a long time is difficult.
Sasatali sir, wonderful presentation.
Thank you, ma'am.
Excellent, sir. Excellent. Thank you so much, sir.
Thank you, ma'am. So I got question, what is the selectivity? So I told I got small amount of ethane and methane. So I think it is around about 90% for methane. You can see my applied catalysis B paper, which is recently published. So yes, any other questions, sir?
Attendees, any other questions? Please put your chat box, put your questions in the chat box. Our resource persons are ready to answer for your questions.
Okay, I think nobody is there. Thank you very much. Thank you to all the Indian friends who invited me. It was a really interesting talk. I have some also affiliation, ma'am, with India. My grandparents migrated from Indian Punjab. So I still remember my village here in Indian Punjab.
Definitely, sir.
Yes.
I feel very proud, sir. I feel very proud. You are our friend.
Yes. Especially South part people, I've seen that they are very good in studies. I am impressed by C.V. Raman, APJ Abdul Kalam.
Oh,
so very interesting people.
Thank you, sir. Thank you.
Yeah.
Sir, I heard so many news about you from our friends.
What?
You are doing wonderful work.
Yes. Actually, I was doing job in industry if you see my CV. So,
Yeah.
but it was my like hobby to study. It was my inspiration to get for higher education, to go for science. So I shifted then industry to. So if a person come with passion, and if the passion and profession, to become together, it's really a magical thing.
Very glad to meet you, sir. You are a wonderful session you gave that.
Yes, thank you, ma'am. I will be hopeful in future we will also have good sessions.
Definitely, sir. Definitely. We'll meet again in the another one webinar, sir. Definitely.
Yes,
We are
sure.
waiting for you also.
Okay, surely.
Over
Thank you.
to Dr. Selvam to propose a vote of thanks.
Thank you.
Thank you, madam. Thank you. Thank you, Dr. Asad Ali sir. Thank you for your
Thank you.
wonderful presentations.
Thank you.
And I am pleased to share one thing. Our
Yes.
institution is marching towards 150 years, and also
Oh,
we got Best Service Award from Chief Minister of Tamil Nadu. That I want to
oh,
share.
oh,
Thank you.
congratulations. Congratulations.
Thank you. Thank you, sir.
My prayer is that your institute must flourish in the future.
Sure, sir.
Okay. And first of all, I would like to thank management team of the MD Hindu College, Thiru Meenakshi Sundaram sir, President, Thiru Selaya sir, Secretary, Thiru P.T. Chidambaram sir, Treasurer, Dr. R. Suresh, elected member, Thiru A.L.S. Mugam, elected member, Thiru D.R. Thirumalayappan, elected member.
MDT Hindu College.
Dr. V. Gomadinayagam and Dr. C. Anida for their support. And also, I thank my colleagues, Dr. D. Selambarasan and Mr. Subhas for their continuous support. Finally, on behalf of MD Hindu College, I thank the resource persons, Dr. Sasad Ali, to accept immediately for this webinar to his busy schedule and his wonderful presentations and also clarify questions. Thank you, sir. Thank you so much.
Thank you, Ji. Bye. Have a nice day.
Thank you.
Dear,
And I thank all the participants for your cooperation during the presentation of this webinar. And we received more than 400 registrations. Thanks for your registrations. We need your support in future events from our college. And dear participants, feedback form will be posted in chat box. You should fill up to 4 p.m. today. E-certificates will be issued within a week only. So the participants who submit the feedback. Finally, a eternal thanks to the internet and God Almighty. And last, quite appreciation is a wonderful thing. It makes what is excellent in others belongs to us well. With this note, B, the Department of Chemistry and Internal Quality Assurance Cells, that means IQAC, the MDT Hindu College, conclude the event. Thank you. Thank you, one and all. Thank you for all. Stay home, stay safe. Thank you.
Bye.
Dear participants, the feedback link will be posted in the chat box. Please fill it up. Then only you'll get the e-certificate. The YouTube link also posted, the link posted.
க்ளோஸ் பண்ணிடலாம். சரி இருக்கட்டும். எல்லாம் வெளியே போக ஆரம்பிச்சிங்களா?
செல்வம் சார்.
யூடியூப்ல
செல்வம் சார்.
சிலம்பரசன் சார்.
நல்லா பிரசன்ட் பண்ணாரு. 40 minutes 40 minutes நல்லா இருந்துச்சு. ஹலோ
ஹலோ
மேம், நான் சிலம்பரசன் மேம்.
சூப்பர், சொல்லுங்க சார்.
மேம் கங்க்ராட்ஸ் மேம், ரொம்ப நல்ல ஆர்கனைசிங், நல்ல ப்ரோக்ராம், நல்லா போச்சு. ஸ்பெஷலி இன்ட்ரோடக்ஷன் ரொம்ப நல்லா கொடுத்தீங்க மேம். ரொம்ப டிபிக்கலா இல்லாம நல்லா இருந்தது.
ஓகே சார், தேங்க்யூ தேங்க்யூ.
இன்ட்ரெஸ்டிங்கா இருந்தது, நல்லா ஆர்கனைஸ் பண்ணி பேசுனீங்க, நல்ல ஃப்ளோ நல்லா இருந்தது, ரொம்ப நல்லா இருந்தது.
ஓகே சார், ஓகே, தேங்க்யூ சார், தேங்க்யூ சார். With your support only we did this.
மேம் எல்லாருக்குமே சப்போர்ட் தான் மேம், அது நல்லா. தேங்க்யூ மேம், தேங்க்யூ.
தேங்க்யூ சார், தேங்க்யூ சார், தேங்க்யூ ஃபார் யுவர் விஷஸ்.
தேங்க்யூ.
Kogilamani madam.
Kavita.
Yes, madam. Thank you so much. I saw your. I'll come with video.
Video on panta.
She's my teacher, sir. Madam.
Kavita.
Me too, video, madam.
Kavita.
How are you, madam?
Fine da.
I'm very proud to meet you, madam. You are my guru teacher. So without you, I can't do anything.
Thank you, da.
Expect you, madam.
தேங்க்யூ தேங்க்யூ.
நீங்க எல்லாம் எனக்கு கத்து கொடுத்த அந்த இதான் வச்சுதான் எல்லாம் பண்ணிட்டு இருக்கேன்.
தேங்க்யூடா. லிங்க் ஒர்க் ஆக மாட்டேங்குதோடா, ஃபீட்பேக் லிங்க்.
Subhasha. Subhasha. Hello, sir. Salam, sir.
Hello. Now feedback from you, ma'am. Hello. You can fill. நான் அது 100 ஆயிடுச்சு, அதனால முடிஞ்சிருச்சு. இப்போ சொல்லுங்க, நான் மறுபடியும் கொடுத்துறேன். ஃபீட்பேக் ஃபார்ம் அது 100 ஆனா கட் ஆயிடுங்க. மறுபடியும்
Hello. கோகிலாமணி மேடம், ஃபீட்பேக் லிங்க் இப்போ ஒர்க் ஆகுது.
ஆன்லி தான் வச்சுருக்காங்க.
Anbarasan sir is online, I think. Anbarasan sir.